Bonn, as well as had previous affiliations at Georgia Tech, Princeton, Cornell, as well as in the industry working for Bell Labs. So among his many accolades, he's the member of the US National Academy of Engineering, and as well as he's a fellow of the American Mathematical Society, of the Inform Society, the Siam Society. He was an invited speaker at the International Congress of Mathematicians as well. And besides all this, he is like a very active and dedicated member of the mathematical programming operations research community. He used to be the editor-in-chief of Mathematical Programming A, Mathematical Programming B, and was the founding editor-in-chief of Mathematical Programming Computation. So before I give him the floor, I want to mention that, as many of you may know, that the traveling salesman problem also has roots here at LSE in particular, as we will hear in Bill's talk, in the work of Elsa Land, who has been one of the founding figures in mathematical programming, and did some early work on this problem, as well as had other key contributions, most importantly on the branch and bound problem. And so Bill will tell more about this, but I just, maybe it's a good occasion to announce that she was selected to be inducted in the Hall of Fame of the International Federation of Operation Research Societies. And this will be announced in a few months in Chile. She is, in fact, becoming the first woman to become member of this very small selected list of pivotal figures in operations research. And with this, let me give the floor to Bill. Please go ahead.
Thanks a lot. It's great to be here in London, and really delighted to be able to speak here at LSE with this long history of working in operational research. So, the traveling salesman problem, or I'll call it TSP for short. It's a thing I'm not on the microphone anymore. Okay, now it's louder. The problem is simple. You're starting and you need to find the shortest route to several of London's top sites and return to your starting point. Right? I mean, that's crazy simple. Except the problem gets more difficult as the number of stops you need to visit grows. Already to find the shortest route to 33 cities can be quite a challenge. I don't have the sound anymore here. They worked on this for an hour. You can watch the video. The sound is great, though, I have to tell you. So he says, "Help the boys." Okay, I'll just skip over. Maybe to fix it later. That was a contest for solving a 33-city traveling salesman problem. You could win $10,000. In fact, 2 mathematicians won the contest. He's saying that to help the boys, salesmen also needed help. That they used guides, such as this 1832 book from Germany, that had a route through the southern Germany. It's visiting 45 stops. What I like is that the author, who was a salesman, gives his personal guarantee that it's short as possible. Right? So it's a traveling salesman working on the traveling salesman problem. I also like that the famed LSE optimizer Elsa Land, her father was a traveling salesman. That, unfortunately, I can't say that motivated her work in it. She was originally attracted to the problem by a van routing, which is quite fitting. During COVID, many of us received many packages at home. Well, those packages were brought to your doorstep by van drivers following traveling salesman routes, sometimes with up to 150 stops. And this routing problem was important enough to Amazon that they ran a contest with a $100,000 first prize. And it attracted 2,200 teams across the world, all competing to try to find a code to improve their routing methods. All right, so those were moving people and equipment from place to place. But the application actually arises in many other contexts, such as in genome sequencing or machine scheduling or data analysis. Pretty much anytime you need to put something in order, there might be a traveling salesman problem. What I'm showing are some companies that have asked for a license to use our TSP solver, which was created with Applegate, Bixby, and Quato. We give the code for free to any company that's willing to tell me how they're going to use it and allow me to also share it with you how they were going to use it. That way I get a new class of application every week or so, which I quite like. But I have to say that the direct application of the TSP is maybe not its main point of interest. The problem is also used sort of as a discussion board for working on complexity issues. So are there limits to computational power? For example, several years ago, the World Economic Forum, this big group of fancy people that go to Davos, they put out a report on the future of supercomputing, and their one-line summary mentions the traveling salesman problem. Or this past March, there was a large artificial intelligence meeting organized by NVIDIA. It attracted over 250,000 developers. Now, NVIDIA is the company that makes those accelerated platforms that support all of those headline-grabbing packages that you've seen recently, like ChatGPT. In the keynote address given by NVIDIA's CEO, he first had this nice graphics about I am AI. I kind of like that. But then he switched to the traveling salesman problem to display the power of their new hardware and software platforms. Quantum computing. We look at a press release from quantum computing startups. This is a big one, $1.1 billion. Or popular articles on quantum computing, even technical articles. They very often mention as their first target application the traveling salesman. Wolfram language. When Stephen Wolfram first introduced this at a big press conference, he had all the algorithms and data structures in the world to choose from, and what he selected was the traveling salesman problem. I should mention that the code that he's talking about here is in fact our Concord solver. We gave them permission to use it in Mathematica. All right, so to me that seems remarkable, that you have this simple problem of just routing a salesman. How did this become the center of the complexity world? It started at an interesting point for mathematicians. Mathematicians in Vienna were part of a larger group of, including philosophers like Karl Popper, who later came to London. Amongst this group, Karl Menger was the leader of the mathematicians, and his star student was Kurt Gödel. Now, in 1930, Kurt Gödel announces his famous result on incompleteness. Well, this same year, 1930, Karl Menger introduced the traveling salesman problem as a mathematics problem. Of course, there's always a practical problem. Salesmen had to find routes. But as a mathematical problem, he describes it geometrically, where the distance to travel is the Euclidean distance, short lines, straight line distance between points. And he asked the most fundamental question, complexity question. You can solve the problem, of course, by just checking every possible route. What he asks is, can you do better than that? So, that's a deep question. At the time, mathematics was really centered on existential questions. And, well, this is not a question of existence. There, of course, exists an algorithm. Just check every permutation. But it takes forever to do it that way. And he's asking whether he can do better. So keep in mind, this is before Turing. This is before any notion of complexity analysis. So I need to define what this means, a huge number of tours. Describe that. So how many routes are there through 5 points? Well, these are circular tours, so I can start anywhere I want. So let's pick a home. Once I have that home, there's 4 choices for the first city to visit. For each of those, there's 3 choices for the next one. So now you have 12 paths. For each of those paths, you have 2 choices to go to the 4th point. Now you don't have any choice, so you have to come home. All right, so altogether that's 4 factorial. 4 times 3 times 2 times 1, which is 24. You notice in the drawing that every item, like the pentagon, each of the shapes appears twice. That's because I'm getting a tour, once going in one direction and the other's going the other direction. So you have an application where the direction of travel doesn't matter, like say geometric problem. then you can divide the tour numbers in half. This will be the application I'll mainly be talking about, is undirected tours, symmetric instances. So there's only 12, that's easy. Yeah, but if you add one more point, you get 60. And you get up to 22 points, you have 25 billion. And this is what I meant by it's huge. It's not practical. The growth in n being n minus 1 factorial, that's growing way too quickly. All right, so you can ask, well, all right, what would be an acceptable growth? Clearly the problem is going to get harder as n, the number of cities, grows. If for no other reason, you have to read that data. The gold standard was laid down by John von Neumann, who solved a relaxation, an easier problem than the traveling salesman problem. He solved it in n cubed time, n to the power 3. N to the power 3 is growing, but it's growing much more slowly than n minus 1 factorial. So we can refine Menger's question and ask, well, for n city traveling salesman problem, can you solve it to n to some fixed power, so n squared, n cubed, so a polynomial time algorithm. This is 1951. Already by 1956, Merle Flood, a great operations research pioneer, starts saying this is impossible. This is not going to be possible to do this. In the mid-60s, Jack Edmonds flat out conjectures you won't be able to find a polynomial time algorithm for the TSP. Now this problem is wound up in this much bigger question, P versus NP, one of the great open problems in mathematics and computer science. I'm not going to go into detail on this, but if you're interested in details, I can strongly recommend this Radio 4 program on this. It's quite interesting. The short version is that if you find, say, an n cubed algorithm to solve the traveling salesman problem, you can earn $1 million. So it's a wide open question. Hollywood has already provided one answer. They say that there is a fast algorithm for the TSP, and that's because that's the more exciting one of the two, what happens. So they see if the sound works now. Oh, that's really bad. This sound was even better. This is great. This is, what's that? You think you can fix it? Please do. The Hollywood made a thriller movie based on the consequences of what a fast TSP algorithm would be.
Gorgeous. Gonna share this quickly.
Wondering when he's fixing the sound, whether it would be possible to also dim the overhead lines a little bit, so that the screen stands out.
No, sorry, still.
Yeah, I'll take control of it again. You think you got it?
Let's try again.
Okay, let's see. No, it's okay. What they're talking about is just over-the-top action thriller. See, if you have a fast algorithm for the TSP, you can do many things, break cryptography systems and things like that. So that's Hollywood's answer. The popular press, though, says that's not going to happen. So the Daily Mail says that to solve just a single 50-point instance will take until the end of the universe. The Washington Post says 22 points will take 1,000 years. In Italy, don't even think about solving a 20-point problem. So all of these reports are because they believe the only way to solve the problem is to go through the tours one by one. And indeed, that would take such a long time. So, all right, so we don't know P versus NP yet. We don't have a polynomial time algorithm for the TSP. But did we at least answer Menger's first question? Can't we do better than n factorial? Well, a first stab at doing that is you might want to replace the number of tours by the number of subsets. So the subsets through n points, there's 2 to the n minus 1. That's big. That's much smaller than n minus 1 factorial. And we can almost do that. So to solve a 6-point problem, tour, what you can do is look at all the shortest paths ending at each of the non-home vertices, non-home points. And the TSP tour is going to be the best of those once you add in the final leg back home. So you can solve the TSP by solving those 5-point problems. Solve the 5-point problems by looking at the 4-point problems. And solve the 4s by looking at the 3s. So altogether, you start with the small problems and work your way up. Never repeating anything, keeping track of what you've done. So how long does that take? Well, there's 2 to the n minus 1 subsets, but each of them has this endpoint. So it's n times 2 to the n minus 1. How long does each subproblem take? Well, you do n additions, because you have to figure out the last route home, and n comparisons, 2n. So altogether, you get an n squared 2 to the n algorithm. Sounds big, but that's much smaller than n minus 1 factorial. And this was found by 2 groups, Bellman and Held and Karp, in 1962. What I find amazing is that that's 61 years ago. There's been no improvement. This is the most basic question about the traveling salesman problem, and we haven't moved it at all. So we're not even inching closer to a polynomial time algorithm. All right, so maybe you can weaken your question. So this is asking for the absolute shortest possible. Can we, at least in polynomial time, get to some guaranteed approximation? Well, the answer to that is no, essentially because there's problems that's either yes or no, there has a tour or not. But for a very natural subclass of the traveling salesman problems, we can get a 1.5 approximation, meaning you're no more than 50% longer than the shortest tour. So this class of problems are the ones that satisfy the triangle inequality, which means it goes from A to B. That can't be any longer than going first from A to C to B. Right? So you don't save things by going to an intermediate point, which makes sense. What distance should you record from A to B should be the shortest distance. Under that scenario, you can get 1.5 approximation. And it's done quite simply. The first step is you connect the points in a tree-like structure. Well, tour also connects the points. So this tree-like structure is not going to be any longer than a tour. All right, now you have this tree-like structure, and then you pair up, you match up the points in a tree that meet an odd number of edges. So the odd degree points, you pair them up. That's called a perfect matching. Now, if you take a traveling salesman tour, it gets you 2 matchings, taking every other edge. So the matching is almost half the length of a tour. So now we're up to 1.5. But now we have a graph where each point meets an even number of edges. So the oldest theorem in graph theory is the Königsberg bridge theorem by Euler. It says that you can then find a walk going through each edge exactly once and covering them all. Then you shortcut that using the triangle inequality to get the tour. This was all put together by Nicholas Christophidi, a long-time professor in London. Again, like Bellman and Held-Karp, it's remarkable. This was done in 1976, 44 years with no improvement. Notice I don't say 47. It's not that I'm bad at subtraction. In fact, there was an improvement in the year 2020. This is by a group of US researchers. They got ever so smaller. It means this is the smallest of epsilons below 1.5. But nonetheless, this was a big breakthrough. It appears in Quantum magazine. I should say, especially here at LSE, several years before that, there was even maybe a bigger breakthrough. It was in the case where the asymmetric problem, where you go from A to B, is different from B to A. That the researchers found the first ever approximation method. And if you need to know that, Lazzi Bey was one of the co-authors of that paper. So I have to say, both of these papers, these are approximation algorithms. These are very important theoretical developments. They're not designed to be practical algorithms. That's why it's amazing that Google actually used Christophidi's algorithm in a real application, in their TRIPS application to design your tours. If you're going around London or around England. In fact, their blog, where they first announced this, they do have almost the same tours I've put up for going around London. And their lead researcher a fellow at Google, Google, says this is a really cool application to Christophidi. It is really cool, but it's also not a good idea. Christophidi is a theoretical result, very important theoretical result, but it gives bad tours. These are examples of what tours are produced by Christophidi's algorithm on 12-node problems, and they're clearly bad tours. Right? They're better than 1.5, but all of them are at least 4% longer than they should be. 4% is a lot of petrol to leave on the table. So if you're designing, you're trying to plan your trip, you probably don't care about any fancy math guarantees. Can you just find a good tour? Well, this is an area of research, actually, is very seductive area of research, right? You just find some kind of algorithm shortcuts. And so there's many hundreds of papers each year devoted to this, and including by biologists, study how various creatures try to find their way around points. So these typically are 4 or 5 points to visit. Like this one is quite nice. It's done in the UK where they put little transponders on bees and see how the bees went from flower to flower, had 5 groups of flowers, and see what route that they took. It's all quite nice. Unfortunately, the articles use solve, and then that gets picked up by the next generation authors that write popular books and say that these are can do better than any computer can possibly do. And this is just not true, right? In no way that these 4 or 5, these animals solving 4 or 5 points are competitive with modern heuristics on super fast computers. For example, with Dave Applegate from Google and Kjeld Helsken from Denmark, very quickly we found a tour through all the million villages on Earth that not 1.5 times optimal, but 1.0002 times optimal, so very close. And keep it with the biological theme, one of the main steps in this, one of the simple main steps of this, it was known to a monkey, Curious George. Again, you won't get the video, but what Curious George you won't get the sound. But Curious George is really upset. Look at him. He's really, oh, no, don't do that. See? Cross. The thing is that the tour crosses. And by Pythagorean theorem, you don't want to do that. If you have a cross, you want to delete those edges and reconnect the paths into a tour. That'll save you distance. All right, then this was worked into a general algorithm by Merrill Flood. He said, well, forget about the geometry. Just try deleting 2 edges and reconnecting the path. If that helps, do it. It's called a 2-op move. And so he repeatedly looks for 2-op moves. So watch how this cleans up this bad tour. Just doing the simple step of looking at pairs of edges, deleting them and reconnecting, takes a bad tour and turns it into a good tour. So this is the mid-50s. By the mid-70s, Shen Lin and Brian Kernighan. So Brian Kernighan, if you're in computer science, he's the inventor of the C programming language. For the TSP, they really took it up a big notch that had this marvelously engineered algorithm that can look up to do k-op moves for even a large values of k. So watch how it very quickly takes this random tour and turns it into a good tour. And that was just the starting point of a long line of successful research in heuristics, going up to ever more complicated local search moves, combining with simulated annealing, genetic algorithms, and many other techniques. And this is all wound up into Kjeld Helsken's code, the LKH. It's the champion code for finding good tours. And it's very, very powerful. The thing is, it comes with no guarantee, though. Right? For your particular problem, you might not have done well. You might not find the optimal tour. So the question is, going back to the newspapers, is it really true that we can't solve particular instances of the TSP? Well, what I find interesting, that work on TSP complexity in 1962, those papers are dominated by practical discussions of computation. Right? They're trying to use that algorithm to solve small instances. And that's the way complexity theories work. They're using complexity theory to back up their claim of practical computation. David Applegate and I made a fast implementation of the good implementation of the Bellman-Held carp. It solves 22-point problems in 0.005 seconds, not the 1,000 years that the Washington Post reported. So it's an improvement. And this is just a start. So there's another whole line of research aimed at solving NP-hard problems like the traveling salesman problem. So complexity theory be damned, right? Complexity theory says that as n goes off to infinity, there's probably some TSP instances that your algorithm's not going to work on. But I have a particular instance that I want to solve for some application. I have the whole raw mathematics behind me. We don't just give up. So this line of research was really started by Haster Whitney, who was a god in discrete math. He invented matroids and other really important concepts. For the TSP, he gave a lecture in 1934 at Princeton. And what he did was take Menger's sort of abstract asymptotic problem and really bring it home so people can really feel it. So he's asking you to find the shortest route where you have 1 point in each of the 48 states. At the time, there were 48 US states. So this is a finite example. And this notion now becomes known, the TSP at that time is known as Whitney's 48 states problem. The first time the word traveling salesman problem appears in the literature is in a paper in 1949 by Julia Robinson. Now, Now, Robinson is a towering figure in pure math. She's best known for leading the team that solved Hilbert's 10th problem. There's a movie made about Julia. As a postdoc, she worked at the Rand Corporation, worked on the TSP, and she didn't look for asymptotic complexity. She wants to know what type of mathematics can be applied to solve small finite examples, like 50 points. Her work had a big influence on the big breakthrough in the traveling salesman problem in 1954 by George Danzig, Ray Fulkerson, and Summer Johnson. They actually solved a 49-city problem, so the 48 states plus Washington, D.C., by hand. Right? They had found the absolute shortest possible tour by hand and give a proof that it's the shortest tour. This is something newspapers say is impossible to do now. And it was also celebrated at the time, so it appears in the Newsweek, and quite a nice article because they're spot on. They're talking about linear programming, which is the big elephant for TSP exact computation. Linear programming, I'm sure if you study operations research, you know linear programming. It's the backbone of the optimization side of operations research. You pretty much can't pick up any product where linear programming is not somehow used in its design, manufacture, or distribution. So Martin Grocho, who is the secretary of the International Mathematics Union, says that linear programming is the biggest contribution of the mathematics of the past century to industrial problems. All right, now, much of this growth and application of the LP can be traced back to this Danzig, Fulkerson, and Johnson paper. They introduced something called the cutting plane method that I'll describe, and that's what's really unleashed it to a wide class of application. All right, so the model itself is simple. Even if you've never seen it before, as long as you're used to matrix algebra, you can understand this. That you're minimizing a linear function, could be maximized, but minimizing a linear function subject to the variables satisfying some inequality or equation constraints. The iconic example it's just a toy example, but iconic example is the diet problem, where the variables are telling you how many servings of food you should have of each food type. The constraints say, well, you need enough calories, you need enough protein, you need enough vitamin A, enough calcium. So you want to meet those minimum requirements for nutrition at a minimal cost. Right? I should say here, you have to allow fractions, so it might be half a glass of milk. Actually, Elsa Lam, when she first arrived here at LSE, this is the first thing she worked on was the diet problem under George Morton. She worked on doing this by hand on not literally by hand, but she had a mechanical hand calculator that she was using the simplex method on such a large problem. I have to say this, I mean, if you like math, you have to like the linear programming. It's almost magical the way it solves these problems. For the traveling salesman problem, this is 100 points. I used the Danzig, Fulkerson, Johnson method to find this optimal tour. All right, now, I don't know if any of you are readers of The Guardian, but our readers of The Guardian here, you would laugh at that claim, right? The universe isn't over yet, so how did I solve a 100-point problem? They say you can't solve 50-point problems. Well, the thing is, linear programming not only found that tour, it finds a convincing proof that it's short as possible. And these pretty colors are the convincing proof. Let me zoom in on it. So you see around each point that I have to visit, I have a blue disk. A salesman tour has to cross that disk twice, so twice the radius of the disk. I also have these other geometric regions, like this yellow band. Well, salesman tour has to sometimes visit those three cities, so it has to go in and out, at least twice, so in and out. All right, so that means the traveling salesman tour has to be at least as long as twice the sum of the radii of the disks plus twice the width of the bands. That's a lower bound on the traveling salesman. This particular example, the tour actually matches that lower bound, so it's the shortest possible tour. And you could do that by getting out a ruler and measuring everything, but that's not necessary. You just need to make two observations. One is each of the regions, like this blue one, is crossed exactly twice by the tour, and each edge of the tour is entirely covered by the regions. You put those two facts together, means that the tour length, those black edges that I've drawn, is exactly equal to the lower bound. So it solved the problem. This is an illustration of linear programming, as I'll try to explain. It was first proposed, this geometric version, by Mike Younger and Bill Poulibank in the mid-'80s. So the linear programming model that I use is called a subtour relaxation. You have a variable for each edge, so each point-to-point connection, telling you whether you're going to use that edge or not, so 0 or 1. You have a constraint for each node, saying that the sum of the edges meeting that node should be 2. Then another constraint for each subset of nodes, each proper subset of nodes, saying the number of edge crossing into that subset should be at least 2. All right, and I use that to generate this picture. Now, you might start be thinking, well, how does he do that? There's lots of those. Right? There's 2 to the n minus 1 subsets. You can't even write it down. It's a 50-point problem. Well, that's true, but that's where their cutting plane method comes in. They generate those inequalities on the fly as they're needed. So to make a simple observation, if you have a potential solution to the linear programming problem, and it already satisfies some constraints, well, you don't need to add them in. Right? You just add them in as they're needed. So what they do is they first solve the problem without any constraints. The black edges, again, are the variables x. In this case, they're values of 2. They're going back and forth. The blue are representing the dual bound. And then they'll gradually add in some subtour inequalities. Get a new solution. Again, check whether all the subtour inequalities are satisfied. If not, add some. So in 8 steps, what I'm showing is how the solution changes, the x variables are changing, and the dual solution, these colorful regions are changing. So after 8 steps, they again have solved the problem. So you have a tour and a bound, just as I described it. So what is really going on behind the scenes is 2 linear programming problems are being solved simultaneously. One is the tour problem, and you're trying to minimize that, those edges, trying to make those as small as possible. The other problem is the bound problem. When drawing those regions, they're also variables, right? You have a variable for giving each radius and each width. And those ones, you're getting the bound stronger, trying to maximize. So you're pushing down the tour, pushing up the bound. And you can never push them below one another, right? This is really a bound. This is known as linear programming duality, very important concept. So every linear programming problem comes equipped with a dual problem, it's called. In our case, the primal problem, the original one is the tour problem, the dual problem is the bound. And the 2 are such you're minimizing the primal, maximizing the dual. You can't push them beyond one another. John von Neumann proved that if you push them as far as you can, they're equal. So yin and yang. And you should thank the computational gods that that's true, because that's what allows us to solve linear programming problems. Right? The 2 solutions certify each other that they're optimal. All right, that allows me to very easily produce these pictures. These are all 100-point problems. Some of them wildly exotic. But again, von Neumann's not lying. The 2 bounds are equal. So you might say, well, that's nice. Why don't you go ahead and collect your $1 million? Yeah, but remember, I carefully pointed out that you might get a half a glass of milk. The same thing is true for this subtour LP. It may be the case that like these edges, these red edges have value half. You're telling the salesman to come into this city and then split in half. Right, so von Neumann, again, doesn't lie. The bounds are equal. It's just that not a tour. I'd have to disturb Danzig, Folcher, Johnson. That is the heart of the cutting plane method. You have these fractional edges are the disease. The cure is to use more cutting planes. So you don't just need these subtour inequalities. You need any inequality, linear inequality, such that it's satisfied by all tours, but violated by your LP solution. You can add that. All right, so that's the heart of their paper. So our heroes must have been really disappointed when they submitted it to a journal, the Operations Research Society of America journal, and the referee comes back and says, those fractional solutions, he doesn't believe that they exist. So this is the whole point of the paper, how to handle those. I mean, we all have bad referees reports, but it's nice the way Folkestone handles it. So a couple days later, he sends in and just points out the 6-point example that has a fractional solution. So you have to deal with it. So what do? They're going to hit it with more cutting planes. The theoretical justification is a theorem from convex geometry, which in this context says that there's a perfect relaxation. There's always the right inequalities to add to the TSP to solve it. So the optimal solution is a tour. So there's always money in the cutting plane method. So again, if that's true, then why don't I get the $1 million? Well, the trouble is we don't actually know what the inequalities are. They just know that they exist. We don't know what they are. Even with 10 points, it's not known the complete set. Yeah, but that, again, didn't disturb Danzig, Folkestone, and Johnson. They just were going to stare down. They know that inequality exists, so they're going to stare down the solution and eventually find, by hand, some inequality that they can add. So now I'll just show the primal solution. As it cuts through, there's 48 states problem. It takes 9 steps. Eventually, they get down to a tour. The first 7 steps are all subtour inequalities. Once they get it nicely connected, they use more exotic ones. These are not what Danzig, Folkestone, and Johnson used. These are from the 1970s, called comb inequalities. But adding those 2 inequalities, I get an LP that gives me the tour. And so we're done. And this was the start of a great expansion of linear programming. and integer programming models used in a wide variety of applications. So you have to like the last line in a Dancing, Folks, and Johnson paper to say, well, maybe they might be useful somewhere else, right? That's modest. This is the most important paper ever written in discrete optimization. For the TSP itself, these are the record size. There's these challenge instances to solve for the TSP. These are the largest sizes ever solved. And you see, in 1954, they solved by hand 49. It wasn't until Heldon Karp, using a different method than what we currently have, finally solved that in 1971, where computers are available. Finally, people understood the algorithm. So Elsa Land also was a major contributor here. I've drawn this on a log scale, so you notice there's a nice linear fit. So since the 1970s, it's been growing exponentially fast, the largest problem. Since 1992, all of the record solutions have been our code, with Applegate, Bixby, Quatel, and myself. And the two largest one also by Daniel Espinosa, Marcos Cuculiella, and Kelt Helsken. The 100,000 point problem is actually a three-dimensional problem. It's a stars in a certain database where the distances are the Euclidean distance in 3 space. These are big problems just for fun, but there's a trickle-down effect. So the largest problem that was solved before our code was some 2,300 points, and now it's solved on this phone, the i12, in 11 seconds. Right, so the time when it was first solved was a big whole day on a supercomputer. Yeah, nonetheless, Italy says don't bother looking at a 20-point problem. All right, well, you maybe have to give them some slack because maybe we've overdone Hassler-Whitney, the get it done faction. That maybe we really greatly overfitted our problem just to those TSP challenge problems. You notice there's only a dozen problems. So in counter, I said that we actually solved 100 million random instances where they were of two types. One in the unit square, where you had random points with Euclidean distance. The other on the torus, random points. So you identify the edges of the square. The point sizes range from 10 up to 2,000. The reason we looked at that was actually like many math problems that come into prominence, there's several different starts to the study. And this was another one from the statistics community, seemingly independent of Menger and Whitney. So the great Indian statistician Mahalalobis, he was also a great man. He was worried about income inequality in India. And he would petition the government to help the farmers, jute farmers in Bengal. And to do that, he wanted to do a sample of the soil quality. And so he had to make a proposal to the government to do this. And the main cost was going to be to transport the people and equipment from place to place. So he had to estimate what was the length, the expected length of a tour. And he argues, roughly, that it's proportional to the square root of n. And it's clear he could have given a proof. He didn't really give a proof. But this was nailed down at Oxford by a team with Gillian Beerwood in 1959, showing not only with expectation, with probability 1, it's going to be the optimal tour. If n is big enough, it's going to be beta times the square root of n, for some constant beta, fixed constant beta. They don't know what beta is. They just gave rough bounds between 0.6 and 0.9. Gillian Beerwood, this was her only work on the TSP. She went on to be a transport economist, working for the Greater London Council, mainly on congestion. She passed away in 2020, so I was lucky that I spent some time, a couple of nights, doing lots of Google searches. I finally found a Gillian Beerwood working as running a newsletter for a church group. And so I sent her email, not expecting anything to happen. But the next day she wrote back, yes, she was indeed this Gillian Beerwood from the theorem. And then she asked this sort of poignant question, so how far have you progressed the problem? Well, like the Bellman-Held-Karp and Christofides, in fact, there has been essentially no progress. Only in the past couple of years has been epsilon progress in their bound. These theoretical questions on the TSP seem quite challenging. So that was why we were doing these computations, to at least say something computationally about the problem. So not proving a theorem, but saying something computationally. So first let me illustrate the theorem itself. So this is a histogram of some 10,000 tour lengths, optimal tour length through 50 points. And I'll show a movie where 50 will increase up to 2,000. What you'll see is the variance will decrease, and the mean value will slowly decrease as well. So the theorem is that this would continue. The BHH theorem is this will continue and finally spike around a given value. All right, and then we use all of those with Applegate, David Johnson, and Neil Sloan we noticed that we could show that this plot was decreasing, which gives you a way of estimating what the ultimate value is. But it's not a theorem, just what we think our computations are given. But what I like about it is we have 100 million examples. We just skip any. It's not like some failed and we replaced them. We solved all 100 million examples. Nonetheless, the Daily Mail said 50 points will take you to the end of the universe. You know, we solved a million examples of 50 points or more, and they said it'll take you to the end of the universe. Again, there's some justification. So why was this in a newspaper? It wasn't only in a Daily Mail. It was in pretty much every newspaper and talk show, radio show in the US. It's because a computer science graduate student had plotted, not an optimal tour, but a pretty good tour through 50 historical sites in the US. And it's just kind of fun. Now, except for 2 small instances, all those other ones are geometric. Right? It's only 2 small instances were of this road type. So you might say, well, all right, maybe we overfitted for geometry. So to answer, Danielle, Marcos, Kelt, and I, we solved not over 50 historical sites, but nearly 50,000 in the US, finding the shortest possible tour. I think the complexity is marvelous. So you have TSP at the high level, but Google's also doing something non-trivial. This is a Google walking distances. This is how it visits the Washington, D.C. mall area. It goes right up to this Washington monument on this curved path. I quite like that. In particular, compared to the only larger 2D example that's ever been solved, that was a VLSI application. When you zoom in, you have all these collinear points. It clearly seems less complex, less challenging, and I can try to quantify that. So when we solve these big instances of the TSP, you could rely on Minkowski and keep cutting, but what happens in practice, you're adding cutting planes and the bound is only increasing by smaller and smaller amounts. So what you finally do is embed the cutting plane into the Land-Duyck branch and bound scheme. So in the TSP, you get a fractional edge, so an edge that has that value half. What Land-Duyck said to do, well, split the problem into 2. Either set it to 1 and then set it to 0. Make 2 subproblems, recursively solve those subproblems. So we recursively apply the cutting planes and split again. That's branch and bound. Land-Duyck are correctly celebrated for these results. So Elsa Land has many awards, including in 2021, the Euro Gold Medal, the highest prize of the European Operations Research Societies. Alison Duyck, now Harcourt, was named the Australian Senior of the Year. Not senior researchers, senior person of the year. I mean, I really like that these two founders of Branch and Bound are so celebrated. Now, and Branch and Bound, I mean, even if you didn't have a weak bounding, you'd still solve the problem, but it again will take forever. You would enumerate all the solutions eventually. So the name of the game is to get a small tree, have a good bounding mechanism. When we first solved that 85,000 city problem, it took us 1,000 nodes in the search tree. Now with our current code, it takes 57, but this US example took 830,000. So completely different scale. So it was a hard problem. In order to warm up to it, I wanted a smaller example. So, you know, I like pub crawls would be nice. I like pubs. And so I went to a database that had like 50,000 pubs, and I took out 25,000 and we computed the shortest tour. And because people like pub crawls and appeared in newspapers. But after I did that, I started getting email. I've got around 3,000 messages and email, like from Matty Boy 19 and Meet, all telling me my solution was crap, right? I should go back and study some other topic, right? And the thing is that I missed their favorite pub, right? And why? It was true. There was 50,000. I wanted 25,000, so I wrote a script, not trying to piss off Matty Boy. Anything that didn't sound like a pub, I threw it out. So TGI Fridays, or if it had a motel or hotel, and I just threw it out. Unfortunately, I threw out most of the places to drink in Scotland, and it's mainly the Scots that let me know this. All right, so I went back. All right, they wanted that. Went back. It took another 2 years of computation, but then we computed the complete tour through every pub in the So Even when you go to the Northern Isles, there's these hard to reach places, you have to take ferries. We include all those. So hopefully Matty Boy 19 and Meep Meep are now satisfied. I have to say, no one wrote back to me, hey, you got it this time. No one actually said that. Okay, so we had to develop a number of techniques to do this. I mean, that's the point of these problems. They're just for fun. No one actually a couple of persons said they were going to start doing this tour, but no one realistically would do that many pubs. But we want to develop new techniques, and one of them would come to mind if you think about it. So Google is doing something non-trivial with those point-to-point distances. So how do they get 50,000 squared of them? Google doesn't give those for free. So in fact, at the time, Google would give you 2,500 a day. Well, you get at home and work, different IP addresses. We were getting like 10,000, 20,000 a day. But you're not going to get up to 50,000 squared. So we put in something I call cost refinement. So I had to make the assumption that Google doesn't cheat. So the shortest walking distance can't be shorter than the shortest distance a crow would fly, the geometric distance. Under that, you can still use them branch and bound. You replace all the Google distances by geometric differences. That only makes the LP value smaller. So that means it's still a lower bound. And then as the run's going on, you gradually ask Google for distances as you need them. So if a variable appears in the LP with non-zero solution, you ask Google for the distance. So asking Google for distance is just a way of increasing the lower bound, the same way as adding a cutting plane or doing a branching. Right? So it's easy conceptually. To engineer it, it took some time, but we eventually solved this with only 2.2 million queries. That's a lot, but it's not 50,000 squared. I have to say, these problems are not solving on your phone. These each took around 200 years to solve if you added up all the computer time, all the processor core time. So it's running on big networks of workstations that were otherwise unoccupied. But you might say, well, you guys should work harder on your algorithm. I have to point out that even low-order polynomial time algorithms take as long or longer. So depending on your coefficient, you might rather use our approach and say an n-cubed algorithm. All right, so pushing on, in 2020, a Dutch firm, once they saw that we had done all this work to get Google, they actually they computed with their computers and their method, their shortest path methods, they computed an entire distance matrix. So visiting all the historical sites in the Netherlands, the monuments, so 1.6 billion distances, they give this full matrix. And again, the short polynomial time algorithm, a low-order polynomial time algorithm would take a couple hundred years, but in a couple of months we had solved this one as well. And again, solved means not that we found a good solution, we found the provably optimal solution, down to the last meter. So this was a cartoon that appeared in the major newspaper in the Netherlands, and that's the number of meters we take. And what it says is, this is the monument to the researchers who found our bike route. All right, so we solved all that. Should we go on? Well, the nice thing about computation, you can always find a bigger challenge, a tougher thing to do, right? And that way might might force you to come up with new ideas. So the state of the art, you should ask Bob Bosch, who has this nice book called OptArt, and in it, he'll teach you how to draw an art picture based on an image with one continuous line, that's a TSP. So he draws a Mona Lisa with 100,000 points. This Mona Lisa has appeared, oh, this also doesn't sound nice. So this has appeared on the covers of books and in journals, and this program called The Strongest Brain appears to tour. And I would like to say we solved that problem, but in fact, no. The approximation has 4 goose eggs and a 1, so I have to point out that commercial solvers, integer programming, they stop once they get the 4th goose egg. So 4th goose egg and a 9, they stop and say you're optimal. So we're well beyond that, but still I think there's more to learn by closing this gap, this small gap. We have similar result for an insight goes back to 2020 that David Johnson made, the year 2000, so it's 23 years ago. It has 100,000 points in a unit square, big unit square. Again, we have a 4-0 approximation with a 3. The last couple of years, Kel Helskin and I have tried a much larger example, some 2 million, a larger astronomical database that's some 2 million stars. Here we actually have 5 zeros in the approximation. And I have to say, it gets difficult to measure things to that type of approximation. So this, our bounding methods are working quite well on these 3D problems. We didn't solve it, and I don't know that we can solve it. But I want to point out in the past 4 years, we have made progress. On these 3 large examples, there's a gap between the Tor and the lower bound. We decrease that gap in each case by around 50%. It sounds great. Yeah, except for Uncle Zeno, right? You decrease by 50% every couple of years and you still never solve the problem. And I don't know if I'll live to see the solution, but I'm certainly hoping that they active enough to finally solve these instances. But I'd say you can always go larger. With David Applegate from Google Research and Kel Helskin, we've gone up by another factor of 1,000. So we're now looking at, or 100. We're looking at problems with 200 million stars. And these instances, you can't run the cutting plane method. These linear programs are really difficult to handle. So what we do is gather as many inequalities and edges as we can, and we just present the LP solver with one LP. Now the simplex method has no chance of solving such a problem. These were given approximate solutions by a LP code that's a first order method. LSE's been involved in some of this work that they have at Google, so PDLP. So they I give them one LP, they give me the solution, I take it back and I compute the exact bound that I get from that. And that's given us already 3 zeros of approximation. So the 100 million node problem has 3 0 and a 1. I'd like to get the 4 0. And that I'm pretty sure that we can get.
They're all in our galaxy?
What's that?
They're all in our galaxy, these stars?
These are...
All in our galaxy? The stars?
Yeah, no, well, they're all of our... They're supposed to be in our galaxy, but you see those bands going out? That's actually because their observations are confused. They're actually looking at the Magellan cloud and thinking those are stars. They're not actually stars. They're just artifacts from it. Yeah, obviously the 3D positions are just their approximations of it. The color corresponds to how close they are together. So all the red ones are close together in the Tor. Well, once you're willing to go up to 100 million, then, well, Google is not interested in astronomy, but Google wants to be able to solve large LPs. So we're currently now working on doing another factor of 10 larger. This is now 1.3 billion stars. In this case, we haven't been able to solve the LP. We just pieced together individual LP solutions to get a dual solution. They only have 2 zeros. But I'm pretty sure we'll get 3 zeros once we get the technology. Okay, so why do we bother doing all that? Well, I just said Google interested in LP. I don't know why they want to solve big LPs, but they do. And this is the way they're learning how to do it through this work. So they want to go big on the TSP. And you should too. I mean, as a community, this TSP research has been very successful as an engine of discovery. So many of the household names in discrete optimization come from TSP research. So cutting planes, branch and bound, local search, simulated annealing, all come from the TSP. All right, but why should you as an individual want to solve the TSP? Well, one thing is you can earn cash. That contest I mentioned, actually we won that contest using TSP methods. So with Kel Helskin together with Stefan Held from Bonn, we won a $100,000 contest and Amazon paid the $100,000. In fact, our team just passing through, actually that's my Wi-Fi that I'm using, so don't break into the Wi-Fi. Our score was actually near 40% better than the second place score. So not only did we win, we won by a lot. And what motivated me a little bit is that, so I'm a card-carrying optimizer, as you know from this talk. But when they introduced the contest, they clearly didn't want to use optimization. Innovative approaches of artificial intelligence, machine learning, deep learning, computer vision to outperform traditional optimization. Well, in the end, we used the traditional optimization just as the type of it's described here and won the contest. So if you want to earn cash, TSP is a good tool. Ola Swenson converted TSP research into a $100,000 help prize. Mainly, his prize for the citations, mainly for the TSP, actually this asymmetric TSP result that LSE was involved in. More recently, Vera Traub from Bonn won $50,000 in the New Frontier Prize. There's a nationwide, it's on national television in the US. This is her ceremony.
Vera Traub works in combinational optimization. For example, traveling salesman problems. Questions like, if you have to make a delivery in several neighborhoods, what is the most efficient route that visits each of them only once?
I'm glad you got all the big words.
Yeah.
Yeah, so if you want to get $50,000 or have Danny DeVito introduce you on national television, the TSP may be your ticket. Or if you want to meet your head of state. These are 5 of the prominent TSP researchers I mentioned, all with either Prime Minister, President, or Chancellor. So you want to meet your Prime Minister, maybe you should work on the TSP. But a more important reason, maybe comes back when a young Nicholas Christovidi told me the story, that he went to a conference in Stanford and met this guy he didn't realize who he was he's talking to, but it was Richard Feynman. And Richard Feynman asked what he's working on and explained the traveling salesman. Feynman went away. The next day came back, yeah, I thought about that. That's a hard problem. Yeah, have fun, kid. Right? And that's right. So the TSP is this easily stated problem that you can really get your hands around, and yet it's capturing enough of complexity that you make any improvements on it, those improvements can branch out to handle many other applications. Richard Karp, one of the great computer scientists, has an amazing portfolio of results. In his Turing Prize lecture, he says his most thrill he ever got was the night that the Helden-Karp, the second Helden-Karp algorithm, started pouring out numbers. Harold Kuhn, he's a famous optimizer, the Karush-Kuhn-Tucker Kuhn. He says he worked on a TSP for 48 years. So there must be something to it. Christoph Papadimitriou says the problem, it's an addiction. And I think that's true. I mean, myself, I've been working on it for now 30 years. But it's not an addiction I think we should cure, just the opposite. Like if I like to get little candy wrappers with little TSP challenges on them and throw them out at parades, right? Because here you have this simple problem, and almost certainly there's going to be breakthroughs on the horizon. We just need to bring in new ideas. So you're all welcome to join in on the fun. Thank you.
Thanks very much, Bill, for this fascinating talk. And so I open the floor for questions. If you have a question, please raise your hand, and they'll bring a microphone to you. So let me collect 3 questions first from the in-person audience, and then we will go for questions from the online audience. So please raise your hands. So we have one here in the middle in the front, and one then in the back after that. Yeah, please go ahead.
Hi, thanks for such a great talk. I just have one question, which is, do you think quantum computing or advancements in quantum computing, if we get to this like theoretical Q day, does that solve the traveling salesman problem?
Yeah, that's a good question. As I mentioned, if you see any of those articles, even for companies trying to raise money, they always talk about the TSP. There's actually no indication that they will be able to solve the traveling salesman problem. Certainly, up to now, they've done little experiments on small instances. They don't solve the problem exactly, but they can very quickly look at candidate solutions. So they do pretty good on like 50 points or so, but not better than current methods. And there's no theoretical reason to think that they would be able to solve the problems. It would be stunning if a quantum computer could solve an NP-hard problem. It just doesn't seem likely. They're very good at factoring in certain ways, but so I think it's only picked, as all those articles talk about the TSP, because everyone knows that is a hard problem, and so it has applications so that they use it. So certainly, I think it's greatly overstated in those popular articles what the TSP. So that I said that the Washington Post said you can't solve a TSP in 22 cities in 1,000 years. That same article, the next line said, and a quantum computer would solve it immediately. That's what they said. And it started in a long discussion on Scott Aronson, runs an important blog on a large, very large discussion, many hundreds of statements all about this. So if you look at Scott Aronson, he's willing to give you enough money to buy a house if you could prove that the quantum computer can solve an NP-hard problem.
Thank you. So maybe our next question in the back. I forgot to say, please briefly introduce yourself when asking your question.
Hi there. So my name is Proshan from a company called Minimax Labs, and we build optimization software. So thanks for the talk. I just wondered, you showed a slide earlier with lots of companies that have used your solver. Could you tell us any of those applications?
Yeah, unfortunately, I can't hear well enough. Did you hear?
Yeah.
My ears aren't as good as the young people.
That you showed lots of company logos, and maybe if you can tell some of the applications.
Yeah, so some of them I like. So Bear wrote to me.
Sorry, but before a related question we got from Gavin Bosland online. Can you use the TSP to solve scheduling problems?
Yeah.
So that's
okay.
Also,
so answer your question first. So so they're all different types of applications. One of them I like is from Bear, because the reason I liked it is the researcher doesn't know what the traveling salesman problem is. He just knows that this Concord solver is part of the deck of things that you're using So it's somehow doing sequencing on genomes that she doesn't know what the TSP problem is, but she can't do her genetics research without it. I quite like those applications. So many of them are actually in scheduling, where you have a machine that has to do different items. Like one guy was making ID cards, so he had to make like 101 cards and certain number cards, and the transition from the travel distance was the transition time from trying to make one card to trying to make the next card. And this is actually one of the Merle Flood, that's what he first got involved in the TSP, was doing machine scheduling. He had these tasks, and he knew the transition times, and he wanted to minimize those. So there's many of them are industrial problems of that type. Quite a few of them are actually just transportation, that you typically have a delivery van that has to go through a number of sites, or there's some nice one, somebody was making a sprinkler system that they had to generate water. Or one of my favorites was in Australia, they wanted to design walks in the park. And so they'd given all the sites some rating between 1 and 10, how nice it was to do that. But they wanted a route of 5 kilometers that visited as many points as they collect along the way. So this is called a prize collecting TSP. So they're nice variety of applications, I find.
Yeah, thank you. Next question, please. Yeah, so maybe in the second row. Nice.
Yeah, maybe quite related to your previous question. Where do you think which areas the TSP is a bottleneck? And if there are advances in TSP, in which areas there may be quite significant changes because of
Yeah, so the easiest one is like Amazon, that they just want to get even small improvements of their van drivings. But the only application, the thing is, most of my work is getting the really optimal solution. And for things like van driving, that's probably not realistic, because you don't know exactly the time it takes to drive it through. So the one class of applications that I know that they really want the optimal solution are in genetics, where they're actually, in the end, the TSP is lining up the genetic material into what they're saying is the genome. Right? It's not like you think they have an electron microscope and they read, that's an A. That's not what they do. They're doing various experiments and then using a TSP to paste the data together. And those ones, they really want to get the optimal tour. They had heuristic algorithms that were producing good ones. They had to run it so long that actually using the exact one sped up their algorithm. So not only found the best tour. So I think certainly in genetics is an example where if you had a faster exact algorithm, that would be an impact. These other ones, getting faster heuristic algorithms maybe is more important than our bounds are doing.
Could you also show this slide with the BBC podcast? Because
Which one?
The BBC podcast or BBC show about TSP you advised, I didn't have time to note it down from your slides.
But I think it was the P equals NP.
Yeah, so they talk a little bit about the TSP, but that is a
okay.
general thing.
Thank you.
I actually spoke with the person, he was going to do a different episode just on NP, on the TSP, but they didn't end up producing it.
We had a question here in the front row.
So I'm Bernhard von Stengel, a colleague of Lazzi at the mathematics department here. So because this problem is NP complete, you could reduce other problems to it. But I suspect that's not necessarily a good idea to reduce a hard problem to a traveling salesman problem and then solve it.
Yeah. I mean, I don't really know. I thought about that of trying to give, say factorization. You factor two numbers. That's an NP problem. To see what type of TSP instances presumably they would be challenging for us to solve. And I think it might be interesting, but I haven't actually calculated how big they are. The trouble is these polynomial reductions are hard. So like a problem like general integer programming is nice because it can capture like satisfiability gets captured into integer programming just one-to-one. It's very, very easy to do. But for the TSP, there's this polynomial blow up. So I'm not sure. But certainly, especially getting factoring would be interesting to me since there's small numbers if you factor. They used to give prizes. I know they still give the money prizes out, but I think that would be interesting.
Yeah, thank you. Next question, please. Like there in the middle.
Hi, Yep, my name's MJ. I'm a final year studying at LSE math department as well. So literally working on the traveling salesman problem, like the very simple version. I'm curious to know, because you showed on the slides that Amazon and whichever companies, they're trying to use different ways like AI and all that instead of trying to do the traditional mathematical formulation. I mean, what are some of the interesting ways that you've seen them try to approach getting a solution from here that's different from what you're studying?
Yeah, again, you can hear better than I can. What was the question?
Yeah, so I guess it's again about the applicability of like AI methods and.
Yeah, so like, what are some of the ways that you've seen companies try to approach this from a like in your slides?
Yeah, so what what companies actually use? As
I don't know companies. Certainly researchers, there's quite a number of research papers over the past trying to use neural networks somehow to predict the next node in the tour. I think it's quite interesting, and I think it's been successful of sort of developing general purpose neural networks techniques. But for the TSP itself, they're not competitive with traditional methods. Whether they will be, who knows what happens 10 years from now, but at least at the moment, the neural networks do not seem to be good. There's just too much structure and too much work that's going on in TSP. It's 60 years of research, and they're trying to do this with a neural net. So far, it hasn't been successful. It's successful for the TSP. It's been successful in generating like transformers and things that are used in other places.
Thanks. Next one. Yeah, in the back.
Hi, I'm Miten. I'm also at Minimax Labs. I was just wondering if you could comment on whether parallel programming has played a role in solving the TSP. So branch and bound is massive. You think that you could parallelize it. Do we see like the linear speed up that we'd expect from parallel programming, or does it like plateau?
I have to get out. Just somehow with the way the distortion on the microphone, I can't understand.
Yeah. So the question was on parallel programming. So how could you leverage?
So most of the parallelism we do is once you start branching, you're having two problems. So we just have one a boss problem and workers. So they're all doing part of the branch and bound search by themselves because they're independent. But then any inequalities they find, they send back to the master problem, and then they can spread it out. So. But our main parallelism, not in the beginning, it would be nice to parallelize the initial cutting plane method for those like 50,000 points. We don't do that. But for the 2 million and the 200 million, even all the cutting plane methods has to be parallelized. So we look around, we subdivide the problem into overlapping geometric regions and are solving the TSPs independently on those ones, finding inequalities and then gluing them all together into one big LP. So without parallelism, we don't. I mean, as I said, those times are 200, and I'm old, but I'm not up there with 100 years yet. The one big open question, actually, is the simplex algorithm for LP. There's no really efficient parallelization for that. The biggest thing computer science could give to operations research at the moment would be a parallel simplex algorithm. There's people working on it, but it's not really making significant progress yet.
Thank you. Next question, please. Yeah, here in the second row.
Hi, my name's Andrew. I'm going to be studying the applicable mathematics masters this year or next year. I'm really interested in how combinatorial optimization can be used in investment finance. So there's a lot of portfolio optimization, but
in finance, you ask?
Yes. So
I actually taught in business school, Columbia, for a year. At the time, the biggest application then that people came to me is that they, like certain bonds and stuff, you had to buy on lots, and so you had these discrete decisions. It wasn't that you could, you have your investment, you couldn't just bust little amounts of money. You had to, I don't remember, but the lot sizes were big, and so they had integer programming models that they were using. I know that somebody so I left Columbia, and the person who took my business name is Sebastian Syria, and he went on to form a company called Axioma Finance using completely integer programming to design portfolios. But What in detail he did, I'm not sure.
Yeah, no, that's fine. 'Cause, I understand they use it quite a lot in like market making. So in the limit order book, they'll use, for example, order routing or allocation. They'll use a traveling salesman problem to optimize, and they'll put the weights on, for example, the paths, the quantities, etc. So I just wanted to see if you had any information on that, but I'll have to do some more research myself.
So allocating?
So allocating like the size of the orders that they're willing to trade with other participants in the market. It becomes an optimization problem at what price level we put what order on, at what point, how do you randomize it?
Yeah, I'm personally not, but I know that these companies that sell commercial integer programming solvers, one of their biggest clients are finance companies. So, but finance companies don't tend to say what they do, right? They just make money, and then they don't. So I don't know in detail, Goldman Sachs or a place like that. I don't know what they do. I know they hire lots of optimization people, but what they do, I don't know.
Okay. And what would you recommend, say, would be quite an interesting research topic or an active area of research, generally in the whole...
You're calling what kind of research?
Just what is like an active area of research, not necessarily in the traveling salesman problem, but overall in combinatorial optimization, which would be kind of an interesting avenue to maybe explore. Or is that quite an open-ended question?
Yeah, I don't really have a good response. Do you have a... It's also a combinatorial optimizer.
Well, there are lots of really nice problems out there, and some recent trends actually are looking at how you can meaningfully combine machine learning with combinatorial optimization, such as using some learning methods as inputs or in interaction with an optimization method. That's for example particularly an active area.
Could you use graph neural networks or something like that?
Yeah, I can say this contest that we won without using machine learning, I think they could have designed the contest which machine learning would have been useful. So we were given 6,000 routes that salesmen, that drivers had used. The challenge was to learn why do salesmen take certain routes. So we're going to get 3,000 new routes, and we're not told them what the salesman did, and we had to get tours, and the measure was how close you did to the driver tour. And we just said with traditional methods, we just thought what would be reasonable things, and we produced tours that were better than the machine learning. But if they'd been given, said 6,000, gave us maybe 600 million tours, so a much larger number. And then rather than actually trying to get the neural networks to create tours, try to get the neural networks to learn rules that drivers like to do. That probably could have been combined in a nice way, but the data just didn't exist. So I think machine learning certainly has a role to play in combinatorial optimization, but for the TSP, it's probably not finding the tours. It's probably finding cutting planes. We don't really have good algorithms for finding cutting planes, but possibly machine learning techniques could do this. Neural networks could do parts of this. So rather than going for the whole thing, looking at certain sub-problems that we don't currently know how to do well. In finding the tour, they're looking at the one point that we actually know how to do well. We know how to find good, we have good heuristic methods for finding a tour, and they're trying to compete on that aspect.
Yeah, thanks. So let's start with the lady in the back, and then...
Hi, I'm Maria. I'm an MSc student in the Department of Health Policy. And my question's more of a personal one. My question is, why TSP? What exactly about it intrigued you so much to work on it for over 30 years?
Yeah, okay, so in the beginning it was that, so there's many combinatorial optimization problems, but the traveling sales problem was always the standard. So if you had a new idea, branch bound was first invented for the traveling salesman. What Dan Doi did was show that, you can use linear programming and make it much more powerful. So if you had a new idea, the way to show that it was effective was to show that you can do something that was a benchmark problem for many areas. So Vashek Kvatel, he's one of the inventor of cutting planes, of particular types of cutting planes. And so we joined in the TSP. We originally thought it would just be one summer-long project. 3 of us went to Bonn. And then we quickly realized, well, it's harder than that. And so then then it just grew. We kept growing, then eventually a year, then a year turned into 2 years, and now 2 years has turned into 30 years. So I have to say, in the health area, in the UK, they actually used our code. At one point, they had nurse practitioners were going to people's homes, and they're doing like, I don't know, 5 or 6 a day, and they wanted our code to just define the optimal route. Not because they wanted to send petrol, they wanted to have the people be able to spend more time with the customers. Not the customers, the people that were ill. And so they at one time broadcast over every home practitioner received a copy of our computer code to schedule all of these nurses.
Thank you.
Thanks. Yep, maybe here in the middle. Yep. Sorry, we have.
Thank you much for the talk. My name is Christopher. My question is, can you possibly combine like machine learning neural network technique with optimization or traveling salesman problems like linear programming?
Yeah, so as I said, I don't know that the traveling salesman problem is a good target, but the simplex method is this workhorse. And for that 2 million city problem, the simplex method was taken 99.997% of the time. And the thing is, the simplex method works from solution to solution. It has a rule. And there's a number of rules, like 5 or 6 that are implemented. Possibly machine learning could come up with a completely different rule, because linear programming, there's many thousands of real examples that people wanted to solve. And you run these algorithms to see the performance. At one time, so I taught 3 times a course, saying it was discrete optimization and machine learning. Or deep learning and discrete optimization. And that was one of the hopeful things I tried to get students to do projects, but it's a difficult topic just for a semester-long project. But I think certainly improving the simplex method would be a target application for. Certain applications, so we can. There's hope for going both ways: machine learning for optimization. But of course, optimization is used in machine learning all the time, just due to back propagation. But I meant at a higher level, of trying to understand what neural networks are doing.
Yeah, and we had another question over here.
Yep, I'm curious to know. You're still trying to solve this and trying to get as close to equality as possible. I mean, what are the approaches that you think is the most promising? And if, let's say, you were to advise, some of the younger audiences here,
the approaches for,
well, to getting as close an approximation, or even equality, if you would give us an advice on which approach you think is very promising that we should look into.
Yeah. So for the traveling salesman, I think at this point, I think it's pretty clear, well, at least this point in history, the only way to solve a large traveling salesman problem instance is these linear programming cutting plane methods. But most of the theoretical research has been on the TSP itself. I think it might be useful to concentrate, to say, no, let's just admit it that the cutting plane method is important and ask for theoretical questions about cutting planes. There's been some small, no, you were not a co-author of the matching paper. No, you were. Yeah. So with cutting planes, algorithms for say the subtour polytope, you give it 1 million points, it runs in like 100 iterations, it solves it. But there's no polynomial bound on that. And there was a very similar problem called the matching problem. And for that, there was a very nice, beautiful combinatorial algorithm. But you could run the cutting plane method on it, but it was not known. And LSE, with 2 co-authors in that case, saying you're very careful what cutting planes you could get a bound on it. And so certainly not for the TSP, getting a polynomial bound, getting a polynomial algorithm running the cutting planes on the subtour would be, that would just be marvelous. Or the other way, this matching problem, I didn't describe the algorithm, it doesn't do the cutting plane method. It does a different way of getting those disks and the bands for the matching. It'd be very nice, I mean, beautiful to have such an algorithm as the matching ones doing it for the TSP. I think both of those would be great, because all these works, they start by first solving the subtour polytope, But even already there, we've already left the world of polynomial time algorithms. So we're nicely theoretically to show that we could do that with the type of methods that we have.
If I may add the question you mentioned on like polynomial cutting plane algorithm for the subtour polytope, that might be a very tough one. Try
Tough.
Yeah,
okay, well that's for you then.
Yeah. Thanks. So more questions? Yes, here in the front, please.
I guess this is probably more of a comment or an observation than a question, but given I'm the last person, I hope it's permitted. It just struck me over listening to your talk that I worked on the census, which was done in the UK, I think, in 2021, and I managed a team of people who were traveling salesmen. They were going door to door with little handheld computers, and the computers told them which address to go to sequentially every day. And
so how did you choose the route? How did you choose the ordering?
The computer chose the route for them,
Okay.
so presumably there was some sort of algorithm behind it, either yours or and then back to street A. And I don't understand why, and I don't want to do it this way.
Yeah.
And my role is essentially say we've got to trust the algorithms, and you need to do what you're told to do.
Yeah. Yeah, so with Amazon in that context, they were giving Amazon drivers routes, and Amazon drivers weren't following them. They were making their own choice, and that was supposed to be part of this contest, to try to get something where we're mimicking the driver's tour. As I mentioned, people keep asking about applications. There's no application for these 3D stars. We can't travel between stars, but I often get requests from astronomers because they have applications where they're taking the telescope and then rotating it to the next spot to see. So they have 25 observations to make at night, and it doesn't matter what order they do them in, and they want to do them as less, I don't think it's a matter of time, it's just that they don't want less wear and tear on the telescope. So they're rotating, slewing around, and so they want to get the order of the observations. So it's, I like the 3D one better because it's challenging. The rotating one is just like a 2D example.
Thank you.